So now to finish up finding the electric field, we'll find the electric field outside of the whole system. So now we'll go outside the conductor. We want to use Gauss's law. So the net electric flux is the integral of E dot dA equals Q in over epsilon naught. Let's just do a quick sketch of the problem again. There's our insulator with radius A. Here's our conducting shell with radii B and C. We want to find the electric field outside, the electric field everywhere. So let's draw a Gaussian surface that has a radius that's outside the conducting shell. So let's draw one with a radius that's bigger than C. There's our radius R. So R is now greater than C, so we're everywhere outside. Let's ask what we're going to fill in here. So the integral of E dot dA, we'll use that same result again that we had before. It's going to be E times 4 pi r squared. And Q in is how much charge is inside our Gaussian surface. So Q in is the charge on the conductor plus the charge on the insulator. Let's ask what those charges are. So if we go back to the problem, it says that the conductor is uncharged, so that has a charge of 0. It says that the insulator has a net charge of Q. So the net charge inside our Gaussian sphere that we drew is just the charge on the insulator because the conductor doesn't have any charge. Okay, let's put those two things together. So the integral of E dot dA is E times 4 pi r squared. That's equal to the charge inside over epsilon naught. We'll solve for E. It's 1 over 4 pi epsilon naught times Q over r squared. And if you prefer, you can write that as Coulomb's constant. And then this part is for R greater than C outside the whole thing. So let's take all of these results, let's put them together, and let's make our graph. So let's do our graph right here underneath our picture because it'll be nice and easy to line things up. So on our vertical axis, we'll put the electric field. So there's our electric field E. On the horizontal, we'll put our distance R, so that's the distance from the center. And then just to help us line everything up, this is R equals A. This is R equals B. And this is R equals C. So inside the insulator, let's go there first. Inside the insulator, the electric field is KQ over R divided by A cubed. It's linear. So inside the insulator, the electric field starts from 0 and goes straight up linearly. So right here, this is R less than A, it's linear, which means that the electric field is proportional to the radius R. So that's inside. Between A and B, so let's go to where we found that result. Between A and B, we said that the electric field was KQ over R squared. So it falls off as 1 over R squared. So it starts right here at this point, and then it starts to go off as 1 over R squared, so it starts to come down. Right here, let's ask about these 2 points. So at R equals A, E at A is equal to K times Q times A over A cubed equals KQ over A squared. At B, the electric field, we can put in our equation, KQ over R squared. E at B is equal to K times Q over B squared. So these are 2 values we have right here on our graph. This is KQ over A squared, and this is KQ over B squared. Then we come to inside the conductor, so that's between B and C. Right here, the electric field is equal to 0, because we know the electric field in a conductor is equal to 0. Okay, so now this part is in the conductor. And then the last part is what happens outside, what happens starting at C. So what is the electric field at C? So we said that our equation was KQ over R squared. So if we're at C, we plug in C for R squared. So right here, the electric field is KQ over C squared. So it would look something like this. KQ over C squared. And then as R gets really big, that electric field falls off to infinity. Now just in case that graph is a little bit too cramped, we can just do another very quick sketch again. So there's our electric field, there's our R. At R equals, so up until R equals A, it's linear. So there's that first graph. Once we get between A and B, so in the cavity it falls off as 1 over R squared. Inside the conductor, so between B and C, it's equal to 0. Then once we're outside the conductor, it continues to fall off as 1 over R squared. So that's what a plot of the graph would look like. Okay. One last point of thing to interest, one last point to look at that's a little bit interesting. At B, it's KQ over B squared if you approach from this side, but it's 0 from this side. Same thing with C. If you approach from this side, it's 0. If you approach from this side, it's KQ over C squared. That's a little bit interesting, and we get those two different values because it's a discontinuous point. So it's not continuous at B and C because depending on which way you look at it, it could be 0 or it could be KQ over R squared.